Okay, so what we talked about last week, we talked about main properties, and so far we had free vibrations. So if you remember in the equation of motion, the PT was 0, so there is no force induced, and we did some examples which shows you how to work with free vibration tests and determine properties. So what we're going to talk about today is we start applying some forces into our systems, and we're starting with something really simple, which is known as harmonic or periodic excitations. So harmonic, they are kind of synthetic. So you're going to see we're talking about sine or cosine curves. Typically, this is idealized. So earthquake loads, they're very randomized. And in a few weeks, I will show you how to deal with such loading arrangement. So starting with, that's where we are at now. So last week we just looked at equation of motions and problems where we kind of pre-disturb a structure and try to determine the behavior. And we had about 5-7 properties which you should be able to calculate based on the examples we did. So structures under harmonic motions, they definitely going to help you to understand the relationship. So we impose or we apply motions into the structures, maybe because we want to pre-disturb it. We just want to know again, with the free vibration test, maybe it's not possible. Maybe the council will intentionally say to you, I don't want you to push that structure because you don't know how weak it is. Because if we're talking about heritage structures, maybe they're very brittle. You cannot really push it by 20 millimeters or 15 or 10. You may break it. So then we have to think about alternative methods, and then we may go and use imposed motions like harmonic motions. That's why they are simplified, right? Again, they will end up giving you the same kind of consideration and understanding, which is finding the dynamic properties. But on top of that, there's other uses which we're going to know about today. So that's what's stated here to you, how the system will respond to other type of forces. So that's basically the idea from understanding harmonic motions. And by the way, we're going to have, this week topic going to go for 2 weeks. We're just going to start with part of it this week. And next week, we're going to do more applications. So we started this week having what we call forced. So this week, you're going to see the equation of motion going to be introduced with a force, not just 0. And it has several useful applications in earthquake engineering because it gives you an idea about how that structure is behaving under a given frequency, under a given amplitude, because as you are imposing the sine or cosine function, you can control these parameters. Right, today, this week, we're going to go through harmonic vibrations of undamped, so no damping. We'll see what's going to happen. We'll see how the reflection is. And then we're going to continue more slides. We're going to have about damped systems. We're calling it viscous damping. So starting with the simple one, no damping, no damping, no viscous damping, no shear frictional damping. That was the last example we did last week, where we had the shear pads. And as we said, it can give us some damping mechanism. So consider that it is not in the system. It's just free. It's just a system under forced harmonic vibration and no damping mechanism inside it. So the force equation now, because we know harmonic motion, looks something like this. Whether you start with a sine curve or cosine curve, it doesn't matter because we're just worried about the response over time. So the forcing equation can be either this or or can be this. Now PO, it is the amplitude. So remember here, we're not talking about free vibration. Don't get confused. Here we're talking about the input into the structure, the vibration we are imposing on the structure or shaking the building with, right? So yes, this curve looks like what I showed you last week, but last week we were talking about free vibration for a structure without having any damping, which gonna look same. But here we're talking about the input frequency, the exciting frequency. All right, now start also to note the properties. So for this type of excitation, or for this type of loading motion, it's got a frequency and it's called a forced frequency. All right, so, and it's called omega. Last week when I showed you the omega, it was omega n. It was with the letter n, because that's the natural frequency of whatever system or structure we're looking at. So today, or what we're talking about now, it's the input force into the structure. So we would call it omega. See, the omega is without any character, without any letter, it's just omega, and it is take it as the forcing frequency. Same thing, you will be having a forcing time period. So T, it is the exciting period or forcing period, like the easiest one. It's just because in the coming slides, you're going to see omega and omega n. Just always understand there are differences. Omega n, it comes from the nature of the structure. It is the natural frequency, right? Omega n. Tn, it was the natural time period. Today, we're talking about the excitations coming into the building. So the properties are written in the lecture notes and many textbooks just without any character. So omega means it's the forcing frequency. T, it is the forcing period. All right, so we agreed about this. Let's keep going. Going back to the equation of motion, right, from week 4. This is the generic equation of motion. And that's right, we got mass by accelerations, velocity by damping, and stiffness by displacement. And this is the forcing function if exists. Yes, today we do have PT exist, and we're going to take it as PO sine WT. Okay, and also we agreed that there is no damping. Damping is 0, it's undamped. So in this case, equation 1 can be simplified as equation 2. All right, that's what we just going through the steps to show you how the solution will look like. Now, before I show you the equation, which is something like this, it's really long and complicated, and you're going to need to go back to math and do it, which I'm not asking you to do in the subject. You just need to understand here we're going to have 2 solutions. With such harmonic, when you impose motions into undamped systems, you will have 2 solutions. One of them is considered to be a particular solution, right? That would help you. You know, in math, sometimes you always get situations where you've got multiple solutions. So when you solve this equation, you will end up having same thing. What does that mean? One of them is for particular solution, and you can see within that solution, it's got the sine function. Now, later on, I will let you what does this mean. I just want you to understand now, there is a particular solution, which is the simple way to explain this to you now. This is kind of representing the force. You can see it's a function of force, okay? Maybe what I can tell you now, when you excite a single degree of freedom system with a sine or cosine wave motion, you're going to actually result in 2 kind of motions in the structure, which will be clarified to you next. And that's one of the solutions is here, and the other solution is there. Now, this solution, basically, you can see it's in function of the forcing frequency. See, with the force. The second solution, you can see its function cosine and sine. Now, the first one is called particular solution, and the second one is called complementary solution. Now, I know until now we don't know what they physically mean. We're going to see that next. Now, if we solve the equation that we started with and use the harmonic motion, we're going to have this very general solution, very long equation. And the first component of it here will give you the complementary free vibration, which was the second solution I showed you before. And this one here will give you the particular solution, which I'm going to come to next. Let me explain this. Let's assume this is your single degree of freedom system. Just got the mass standing on a stiffener, like a column. And also there is a damping system, because that's what did we say there's no, we said there's no damping. So let me just delete it. Don't worry about it. So here you've got a column with a stiffness, and here you've got mass, and you're actually applying a force here, which is the harmonic motion. Right, what's going to happen to this structure? It will first vibrate with this shape. So it's going to vibrate left and right, and that vibration will keep going like this forever. So imagine that the forced vibration, the red one here, it is represented. I should have been using the red color to make it clearer. So, you know, the shape of vibration, the red one I'm showing here, it's actually going to be the shape of vibration the single degree of freedom system is shaking at, and it's going to be ongoing. It will not go away, right? What's about this complicated complementary free vibration? While the system is going to the left or right, it will be again shaking by its own. So it's difficult to draw it for you, but as that single degree of freedom is moving, it is by its own also shaking while it's moving. That's what's really happening to it. Now, the main one, it is actually, as you know, the one which is developed from the forcing harmonic motion. The second one, which is kind of shaking as it's moving left and right, it is a free vibration, which we know in reality it should go away because there is damping. I know at this stage we're trying to talk about undamped systems. That's what we said in this section. But this is just for you to understand the theory and the concept. But in real life, we always got something to damp a vibration, whether the air, even the air itself can resist motion. So what I want you to understand from the solution of this equation, the solution is complicated, but we're not doing the math here. The good news for you, we're not doing any math. The solution in the end of the day gonna look something like this, right? What does it mean? The simple part of the equation, it represents the forced vibration of the system, how the system gonna react to the forced vibration, and the system will always keep going left and right. Number two, you got this complicated side or part of the equation. It is called the free vibration or complementary free vibration. While the system moves left and right, it's gonna be shaking by its own. This is yet minor motion or vibrations, which ideally will go away because it's going to be damped. It's free vibration, it's not kind of forced vibration. So let's see next. These curves will help us to understand it. So we're using this equation and we're trying to plot it in Excel. So this equation, which is the equation number 5, the one which got both complementary and particular solution. So the particular solution, as I said, it's representing the forced action. You can see the P here and the sign function there. We're assuming that the forcing frequency over the natural frequency is 0.5, just assuming a number so it can help us to plot it here. And we assuming that the initial displacement is this figure. Yeah, that's where we're starting here. And we assuming the initial velocity is again another figure. So it's just the constants we're starting with, which really doesn't matter. We just want you to see the response. This is the response, how the single degree of freedom system gonna respond over time. Now you can see here the sine function. As I said to you, it's kind of the only one represented in the forced vibration, which means it is the forcing motion, because we started with forcing the system by this function anyway. And you can see these functions are located within the forced vibration. So how the structure is responding, you can see this is the solid line, is the overall response of that system. That's what I was talking to you. I was talking to you, the system will go left, right, left, right. And while it's going to the left and right, it's actually vibrating as well. Now, the main motion, left, right, okay, it's just gonna continue always, forever. Why? Because we have a forcing excitation, because we have harmonic motion, unlike last week. Last week it was free vibration. You just displace it and leave it. No force anymore. But now we have harmonic motion, always gonna be forcing the system to keep going left and right. What about those vibrations? Yes, they are free vibrations were generated because of the initial inertia that made the system move. Okay, and if there is damping, somehow they will go away, which as we're gonna see next. Okay, so the solid line, basically, which represents the main motion, is typically taken as the steady state response. Why steady state? Because it's excited typically by the function, by the external force. So this slide just reconfirms what I talked to you. There are two types of excitations involved. One is the the forcing vibration, and one is the free vibration. That's just reconfirms or re-explains what I've took you through. And again, the first one, talking about the first one here, is the free vibration or transit vibration, which depends on the initial displacement and velocity, how strong it was pushed initially or displaced, if there was displacement. The second component, which is this, it is the forced vibration or steady state vibration. So there are different ways to call them. You don't need to use both. And it represents the applied force. So it's actually continued and gonna stay steady, because you got always the harmonic motion imposed onto the mass of that system, right? So, so far, what I want you to understand, this simple equation of motion, which we can simply define for a single degree of freedom system without damping and being under harmonic motion, can be solved mathematically by this lengthy equation. And what does it physically mean? The first complicated part, it is free vibration mechanism. Next, when we start talking about damped systems, we're going to see how it will be cancelled or ignored. The second part is the critical one or important one, because it's going to stay there forever, and that's really what we're going to use to do what we have to do this week. So next slide, again, have a look to this note here, just talking about the same transit component. Transit component, which is the free vibration, yeah, is shown as different. So the transit, basically, the transit, if you subtract this response, the steady response from the transit, it will represent that free vibration. And this is only an academic point of view, because the damping invisibly presented in real structures, that's what I was talking about, and makes the free vibration decays away. So all those vibration will actually go to zero, and we can easily cancel them. That's why they can sometimes call this free vibration transit as well, because it's temporary happening. It's not continued. These ones, the shaking I was talking about while it's moving, it will go away from the system. Okay, so that was about the harmonic motion, exciting single degree of freedom for undamped system. Let's see what's going to happen when we have now damped system. When we have damped system. Same thing, we go back to our equation of motion, but now we will keep our damping in business, right? Then we're going to go through math and solve it, which again, I don't want you to know about. I just want you to understand how it's really working to build up the physical meaning of it. Then after this, so this is the solution, right? So have a look here. What did we say that? Was this the free vibration or it was the forced vibration? This part here, highlighting. Is it the free vibration or the forced vibration? This part of the equation, was it the free or the forced? Yeah, if you remember here, the first part was typically the free vibration. Okay, so the interesting part in it is you do have the damping related to it. Okay, and that means it will go away at some stage. All that will end up being a zero because it will be damped somehow. And the one that will stay with you is the steady state, is the forced response. So again, this is the solution. And again, I don't want you to worry about the deviation, but if you want to really go through, it's in the recommended textbook. And if we go and find or assume constants for these A, B, C, D parameters, and then try to plot it to understand its physical meaning, that's what you will get. Okay, so we set up some assumptions to help us plot this equation, right? You will find this plot. And the interesting part is, you know, those shaking mechanisms, the secondary transit or free vibration motions, they will end up going away and you will end up with this steady state response to actually present the actual response. And that was the point we mentioned. So comparing this again with the undamped case, not sure if we have it here. Here we go. So this slide shows you a comparison between the situation where we don't have damping and we have damping. You can see the difference here. So before we had vibrations ongoing, but it's not a real situation. We're always going to have some sort of damping. When we have such damping, it will end up just the curve or the response or how the building can react will react in line with the steady state response. What does that mean? This part of the equation will be what we want to solve, and this part of the equation will be used to determine what's the displacement over time. That's it. So let's go and find the final answer from this. This is it. This is where we can get the final answer, which is also presented. That's actually the two main equations you want to understand today and know how to use. These are basically. So the first one here, from the second part of the equation, equation 6, which is this one, you know, that the other side, which we said it is transit. It is not the transit will be 0, but the steady state response, it's represented by the second part of the equation. If we rearrange and solve for displacement, we will have this answer. We will have this answer, which can give you the displacement over time in function of the static displacement multiplied by RD value, which I will come to next, and also defining by the lag angle. We'll talk about this. What does RD mean? RD is the deformation response factor. It is basically the ratio between the dynamic response to the static deformation. So there is always static from whatever you studied. Static deformation simply is the force divided by the column stiffness. That will give you an indication for a static displacement. So if you know the maximum amplitude force from your problem or from the harmonic motion, you would know the, like if I go back to any harmonic, this harmonic chart, this one, we know what's P, right? Because that's what we're gonna input into the structure. Okay, and we also will be able to know the stiffness of the columns. Then both of those parameters will help you to figure out and estimate the static displacement, right? Static displacement is not always same as the dynamic displacement. Dynamic displacement can be longer, or typically is much bigger or longer or higher in terms of value. Now, who can relate, or how we can relate the static displacement with the dynamic displacement? UO, it is by RD, the deformation response factor. So the deformation response factor is just simply the ratio between the dynamic response over the static response. And to simplify this equation, we have introduced it in the solution. Right, so from solving this side of the harmonic equation, or the equation of motion when we involve harmonic motion and also involve damping, we can have such answer. You can see the damping is not in the equation now because it was with the transit side of the equation. Okay, so equation 8 is kind of the key equation we're going to be using in what we're doing today and next week as well. By rearranging equation 8, we can actually have this kind of much more friendly relationship where you can directly say find RD, which is the deformation response factor, defines this ratio, dynamic over static, can be defined as shown here. And it was possible to also include the damping. And we will see next how critical can damping be. Sometimes it's not critical, sometimes it's not. Because damping was involved within, damping can be related to the constants we have in the equations as well. The phase angle, so the phase lag angle, right, which shows you how far the peak of the action. We're going to see some curves. So this is, again, I think that will help me to explain what lag means and what the RD means. So here we got 3 different type of comparisons between static response, right, and the dynamic response. So the static response, typically it's going to be unified because it's just same always. And the actual dynamic response, that's what the building going to feel. It will be the actual one that we try to calculate because that's the one we going to give us what's happening with the building. The static one is kind of unreal. It's just because we're assuming the force is going to be placed on the structure and stay there statically forever. This is not a real representation of the situation, but it can help us to do calculations for the dynamic deformation. So the RD basically is just presented in the vertical axis, and simply it will define the peaknesses in those curves. Right, so this shows you again what's the RD value for the dynamic response. So the RD value here was 1.29, sorry. Okay, now what was the lag? The phase lag, it is the difference at a single point between the static and dynamic situation. So you can see here the static starts from 0 and also gonna be with 0 RD, but the dynamic is different. The dynamic will start from different response, and it will be at the same RD value with a lag in the phase angle. And here the lag is quite small. Okay, so basically the 2 key things you really want to understand and how to use in today's lecture is you need to know how to define and calculate the RD values and the phase angle. But I can tell you the most practical, or what we use mostly in evaluating the dynamic behaviors for structures, is we use RD. That's what we mostly use. We use RDs in our calculations because this kind of make more sense. RD will help you to answer more structural engineering problems, but phase lag really doesn't matter when the building gonna be at its maximum left or when it's gonna be at its maximum left. This is not a problem we always need to investigate. What we need to investigate is what's the actual displacement that was developed due to dynamic excitation. So before we start like solving problems and showing you, today we have only one example really to do. But before we're gonna use this tomorrow or next week, and we're gonna have more examples during the workshop, we'll just try to examine those curves and understand what does it mean when we keep changing parameters. So over those charts, what we have fixed the damping. So we have a system. We have 3 systems with fixed damping. And what we changed the ratio between the forcing frequency and the natural frequency. And see, we started with 0.5. So the forcing frequency was half of the natural frequency. And B, it is the forcing frequency, same as, which you all know this means resonance. This means there's a problem. And obviously you can see how severe the RD is. It's 2.5 times. This kind of telling us this is 2.5 times. So if you calculated the amplitude to be 1, the static amplitude to be 1, your dynamic response will be 2.5 that value. Okay. Now, so they saying that's if we have resonance. If your forcing frequency was same as the natural frequency, you're gonna have quite large displacement response factor. If your forcing frequency is half of the natural frequency, then you can see we do still have some increase. RG will amplify the system, but it's only 1.3. The best solution, like the most reduced amplification we can get to, is when your forcing frequency is actually 2 times, so more than the natural frequency, because you don't feel it. You know, if you go very high frequency in a structure and the structure was very stiff, you won't feel it. And this is exactly what they want to do when they want to reduce the tram lines vibrations onto the neighboring buildings. So usually if you got a tram line, it's going to cause vibrations. And what they do, they're going to try to play with the stiffness of the structure in a way, which is usually the case. It's just a check they do, because a building near a structure, it's got very high stiffness. And usually if you managed to make sure that the stiffness will result in this ratio, then imagine that the dynamic response will be very, very small and it won't be a problem. And that's really the situation. That's why sometimes when you sit in a building near a tram line, the building is okay, but the only problem with the glass, with the window itself. Maybe you hear some vibrations or noise from the window only. And that will happen even in your houses. When a truck moves next to your house, you will feel the windows usually, because windows are much thinner. And with windows, you may get here, the window itself, the window element. But the whole house, usually their stiffness, their natural frequency will be much, much lower than what the truck is doing, or a tram is doing in terms of the vibration that's coming to the building. So it's kind of the same. So try to, when you review these notes, to try to really imagine those curves and see when we're changing this ratio, what's happening to the amplitudes. Is there any question about what I'm talking? Okay, I will start asking you then in the coming slides. So in this slide, basically, we just we're gonna have other situations to investigate. This slide is basically redefining to you what the lines are. So as I said, the dashed line, it really represents the static behavior of a system with ignoring all the dynamic responses. So it's just simply telling you, just taking this static ratio and try to distribute it via the harmonic motion, the sine curve. And basically we're comparing it with what the dynamic get to, and this curve, it's coming from that lengthy complicated side, the steady state answer of the equation that I showed you. And we ended up finding that when we have resonance, the forcing frequency omega is same as the natural frequency. The damping, the deformation response factor can be beefed up 2.5 times the static response. So it's quite significant. Right, now this slide is just defining, talking to you about the lag. So as I said, the lag is just defining the differences between same points. Here, if you got a peak, this is where the dynamic is peaking, and this is where the static is peaking. So this distance usually is the phase lag. Practically, this is not really a problem structural engineers would be investigating. Like maybe other engineers, if they working with, those electronics, electric people who works with frequencies and telecommunications, they may be interested to find that lag because it does improve or decrease the quality of the sound, wherever they do it. But in construction and building and framing, it doesn't matter that time. The main thing we investigate, and you're going to see we mostly calculate in our examples, is the RD values, because that will tell us how far your building going to actually be displaced. And this is what we need to know. This is what we always want to know, because it will then let you design the building correctly. Is the displacement, how much it's really going. That's what we're really after. Okay, so there is another way. I think the last, there is another way to investigate. There is another way to investigate to kind of examine the sensitivity of those RD values by using what we call a frequency response curve. Frequency response curve is just another curve that dynamic engineers use a lot. Even when we go on and buy some accelerometers or tools we use in experiments, they always going to show you in manuals and instructions a response, frequency response curve. Now, frequency response curve, simply, what does it plot? Plot the two relationships that I talked to you about. The first one is the RD. So the vertical curve, typically here, this one, the vertical axis, it is the RD value, which is the ratio between dynamic over static. The horizontal axis, which is here, it's the frequency ratio, forcing frequency over the natural frequency. And the results here will show you a relationship between RD and the frequency ratio for different damping values. Okay, and we can examine them step by step in the coming slides. So we will be using those kind of and solving some of our problems, or we will ask you to plot them sometimes. But they are like very useful for dynamic engineers to understand how the building or a structure is actually behaving. So if you've got this plot for a range of RD values and for a range of frequencies, this plot can be easily used to answer many questions or different type of structures within a building or the building overall. Because if you, by the time you know the forcing frequency and you will be able to calculate the natural frequency of the building, you should be okay with this ratio. And then it depends whether you want to find the dynamic. You can use this curve in a reversed way, or maybe you want to see where does it sit here and find how critical it is. All right. So we do have a number of cases that we will be examining, and then it will help us to determine the different situations the exam structures can be at. So you can see again, the plot is shown different lines for different damping ratio, and as we discussed last week, the damping ratio can come from those basic equations, which we said last week. It's the ratio between the damping constant over the critical damping, or critical damping is defined by 2 mass by the natural frequency of the system. Okay, so that's just kind of explaining to you the details of those plots. And next, we're going to be examining what's happening there, which is shown on the slides. So we have here for you different situations. Let's start with the first one. Let's say if the frequency ratio, omega forcing frequency over natural frequency is way less than 1, like very small. Can you guys think with me, and let me do kind of an exercise here. What do you think here? Which one is vibrating? I just want you to practically imagine these kind of values, not only just looking at the numbers. So what does this mean? I'm trying to make sure you understand what does this mean here. When we're telling you the forcing frequency over the natural frequency is way less than 1, what does it mean? Let me help you with the question more. So let's say you got a ground here. This is the ground. And you have a building. Right? You've got a building. Okay. So you've got a harmonic motion. Let me say it is with color red. Which will come with particular sine or cosine motion, right? So what do you expect the building will have? More kind of closely spaced vibration or larger spaced vibration? Or alternatively, do you think the building will have this kind of vibration or even more gentle? I just want you to imagine which one's going to be, 1 or 2, the building, to represent the situation we are at. So the purple represents the natural frequency, yeah? The purple color represents the natural frequency, but I want you to answer me whether number 1 or number 2. And the red, it is the forcing frequency. So which one you think will apply on this condition 1 or situation 1 we are talking about here? Number 1. Yeah, so the frequency here, number 1, is way higher. That's correct. Yes, thank you. So you can see from number 1, from the graph, you can see there is very high frequency, right? And it seems to be much higher than the natural frequency, the red one. And given the Forcing frequency gonna be less, so we're gonna be less than 111. So just let me check the answers. Do we all agree? Okay, so the forcing frequency, this one is much, much higher than, sorry, the natural frequency is much, much higher. Let me just put the wording so we don't get lost. The purple one is the omega n. And the red indicates the omega. This is the forcing, because the red one is coming from the ground. The forcing frequency is coming from the ground. And it is much smaller than the building. Okay, so let's see what does this mean. If we have a situation where, okay, can I ask you, do you think the building gonna be really stiff or cylinder? I just want you to build more imagination here. Do you think which building, so this is another building I'm drawing for you. Just we take it step by step. I'm gonna make another skinny building here. Skinny building, yeah? Which one you think will be with higher frequency, natural frequency? Which one? Okay, you've got here two. I would have been using a pen, but let me just clean things for you. So again, we had here a vibration with a lot of frequencies, and I've got an answer telling me this first frequency, number one, comparing it with the forcing frequency W, omega, the red one, it's actually put us in this situation. Correct. But I'm asking you, imagine with me now you have two buildings, one skinny and one large. Which building should represent number one, and which building should represent number two of the natural frequency? Which one you think gonna be vibrating naturally with a lot of frequencies? Is it the wider building? Correct, well done. So vibration shown by the graph number one gonna be applied on the wide building, because usually wide, short building, they have really high stiffness. And that means the frequency gonna be really high. Connect what we're studying today with what we're studying last week as well. And this building number two, it will be skinnier, it will be kind of waving more than, like, try to imagine always those numbers. Don't just say, where is the equation? Let me get the answer. Try to imagine those numbers. So the skinny or tall building, its stiffness typically will be less than number one. Eventually the frequency will be way bigger. So in our scenario here, case number one, we are in a situation where we've got really a stiff building standing on gentle vibrations, put it this way. That's where I want to get you to. Don't just read those characters, because when the question gonna come to you with the practical intentions. Okay, so this situation represents basically a stiff building being vibrated by a gentle motion. Okay, and again, the notes here try to explain it in a different way. So if the forcing frequency over the Let me delete that so we have a cleaner page. So if the forcing frequency over the natural frequency is way less than one, which means that the forcing time period is way bigger than the natural period, which means the force is actually slowly varying. That's what I'm trying to say, but in a practical way. I'm trying to tell you, in this situation, you've got a stiff building being vibrated by a gentle motion. In this case, we're going to be conditioned by this location. Let me delete that now. Take it away. We're going to be within this arrangement, right? Because our ratio is very small. We are very, we are just here. Okay, and what does that mean? We have no relationship with the damping. You can see, because all the lines are matching here. All the lines are kind of coming together. So there is no relationship with damping. It doesn't matter. If you spend a lot of money on bringing damping, it won't really matter. And basically your dynamic response will be approximately equal to the static response, which is very simple solution. You just go back to statics, you studied your undergraduate level, or maybe at school you studied this equation, and that will give you how many millimeters the building will be swaying at if it's hit by this gentle motion. So again, when you have buildings, stiff buildings being excited by gentle harmonic motions or gentle motions, then basically the displacement that will be resulted on your structure from such motion will be equal to the static displacement. Simply just go find the peak value of that curve and divide it over stiffness. As easy as this. Okay, so that's the first condition. Second one. Here is the other way around. Okay, here you've got very soft building. Oops, sorry for jumping the slide. So the second condition we have here, it is a soft building being excited by very high varying, or not sure, I don't want to say gentle. The opposite of gentle will be very sudden motions, right, or very shaky ground excitations, or maybe I can say the ground excitation is with very high frequencies. If I go back to my diagram, I mean, so you can imagine it. This is your ground floor, and you have here a skinny building, and the vibration, sorry, let me do it better. The vibration is like this, and the building, the natural frequency here will be a bit gentle. This is the second situation we are in. So you got a building which is natural frequency omega n is kind of gentle, and the forcing frequency is with high frequency, very high frequency. In this case, what's going to happen with us is that what's going to happen with us is we're going to be situated here within the frequency curve, frequency factor curve. Right, because we have very high ratio. So if you divide the frequency of your natural frequency of the building, or the other way around, if you divide the forcing frequency of the earthquake or the harmonic motion over the natural frequency of the building, you will end up having a high ratio value, that omega forcing over natural omega going to be really high. And in this case, we're going to be at the very right side of our response curve. Think about it. What does that mean? It means that your amplitude, right, your deformation here will be very close to zero, which is also good. Because your building, that's the example I was talking about for the tram. You know, the example for the tram or for the truck. The truck, if you go, you're gonna see, or the tram, basically, it's gonna cause a lot of vibration, but the frequency of those vibrations are very high. The building won't be sensing it, won't feel it. Okay. and which is working to our advantage because the dynamic is telling us this, and we're not kind of impacted. The mathematical reason for that is coming from this kind of relationship here, because in this situation, we will be working with this equation. We're going to be dividing over the power square of the frequency. You can see here, we're going to be squaring the frequency itself. That's why this is going to give us a very high answer, and we end up with very, very small amplitude. So your response, your dynamic response will be insignificant. Okay. And basically, that's what I was saying. It is controlled by the mass. The vibration is controlled by the mass, and here the building, the mass of the building itself is kind of leading the show. And yes, there are high vibrations that can come from tram lines or the tunnels from the trains under the ground in the city. But those vibrations, yeah, sometimes you can sense them if you walk next to them, but the building won't really shake because of those vibrations, because of this relationship, because the ratio between the forcing frequency over the natural frequency is way, way above 1. And when we are sitting here in this side, see what's happening with your RD value. It's kind of nothing. It's a little bit above 0, a little bit above 0, which is not a problem. So we are just a fraction of a response. So it's not a problem. Right, so that's really the idea. And if you need really to go and calculate it, you can simply use this relationship equation 12. And you can see whenever the frequency, the forcing frequency increases, you still gonna have your displacement even more. And same thing, the damping don't have any impact. The damping, so if in math we found that the vibration won't be affecting the buildings, we don't need to put any insulations or damping mechanisms, unless, you know, sometimes, usually, as I said to you, the glazing can be affected, the glass or those canopy features there, because they are kind of much weaker. They may be here. They may be under the third situation, which I will explain to you here. That's the critical part here. But the good thing, it's always when you are close to 1, which with your design, you can always play with it. You can always push your frequencies. You can control your design, but you cannot control them. It's difficult to remove the tram line or the train or stop an earthquake. You don't know how it's going to be coming. So, but you can play with the structure itself. And your aim is to try to put it within this zone or this zone to prevent the resonance. So this third situation here, it is basically the resonance situation. And when it's going to happen, it's going to happen when your forcing frequency from the harmonic motion is same as your natural frequency of the building. If you were really not lucky, and that's really, as I said, the glazing mechanisms, like, yeah, canopy, the glass. I'm not sure if you know really what I'm talking about. Anyone can tell me what I'm talking about? Try to find your picture. Okay. Yeah, like these kind, but here we go. You know these things? These are usually needs careful dynamic, like these kind of things. You see them, they are just, they are all the way around in the city, and they're very sensitive to vibrations. And the building won't feel any vibrations, but these will do. And that's where you can introduce some dampers, just some rubber, to actually absorb all the vibrations. So what I'm trying to say, these kind of more affected, if you go and design them, go do the calculations, you will find their systems lying around, because the frequency from the road, from traffic, or from train or tram lines, they can be very close to their natural frequency, unlike a building. A building is stiff, it's really large, and the properties of concrete can help making the system somewhere here. So it doesn't matter. So no impact, no resonance. And eventually your RD gonna be small. That's the good thing. It's only when you have resonance, your RD can go very high, and that's the problem. So if statically you calculate that glass system will be sagging, what will be sagging 3 millimeters, which is not a problem. Dynamically, you multiply this 3 by 5, which is 15 millimeters is a problem to sag glass. Glass will just break. Yeah. And you know, you see when any accident happen, or it's usually the glass will give up because it's very sensitive to displacements. So what do you really guys need to, before the end of this week, before we start next week, I just want you to carefully run through. You don't need to do any math. You just need to understand this equation from here, understand where is this coming from, then understand this equation number 8 will be rearranged to introduce for us equation number 9. Then try to physically understand it. I will not just give you a question where I give you the static and RD, then ask you to find a static. You know, anyone can do this. You don't need to do a master, right? You're going to be asked real questions about those properties and what do they mean for a real building being excited by a real harmonic motion. And I've been discussing this over the past 20 minutes or so. So after you look at those examples, go through these slides, understand the different responses that we have from each assumed system, and then understand what we mean with the frequency response curve. Is just another representation that engineers like using, or another graphing technique that engineers like using to determine how critical their structures are against particular motions. That's basically it. And you may ask me, how do they do these curves? They just use Excel. They just keep changing the, for example, the damping ratio, and they keep changing the properties here over time. By the way, in week 8, I will let you do something like this. I will let you actually generate what we call a response spectra curves for the building you're designing, you know, assignment 1 building, which I think you're working very well on. I'll talk about it next. You're working on building 1. I will ask you to develop response spectrum curves because we can't use equations when we have real earthquake hitting a building. We have to do something like this. Okay, so I will. You will kind of have some experience how those curves are developed, which is simply just using math, time differentiation process, and you will be able to plot them. So what I want you to understand from today's lecture is know about this frequency response curve, understand its axes, what the vertical axis physically mean, and what's the horizontal axis physically mean, which is simply the ratio between the forcing frequency over the natural frequency. I do have students in the final exam keep mixing these ones. In the question, we tell them this is the forcing frequency, and they think this is actually the natural frequency. They still don't know what's the difference between forcing frequency and the natural frequency. And that's just a major mistake because everything else is going to be wrong. So go through, this is just further explaining what those charts will be about, and try to go through this kind of examination for the response, for the frequency response curve. try to go through this examination. Understand what does it mean for a building to be situated here. Understand what does it mean for the building to be situated here. Understand what does it mean for a building to be situated at the very right of the curve. So yeah, now as we done with those three situations, we do have the last few slides talking about what the phase like, the angle. Same thing with the angle. Yeah, we understand from the previous slides that the RD, or the displacement response factor, is very sensitive to the frequency ratio, right? We found how sensitive the RD value, this is the RD value, to the frequency ratio. And I did show you some examples. What does it mean when you are here? What does it mean when you are there? Etc. Same thing. The phase angle also kind of sensitive, although I did tell you it won't really matter a lot for the engineers. I really, in even that canopy designs, nobody will care about when the glass will be amplified or when the those shear lags or the frequency lags, when they're going to reach their amplitudes compared to the excitation. That's not really something we study or try to evaluate. As I said, this is maybe something telecommunication engineers will worry about when they study how to transfer data through the Wi-Fi or whatever they're doing. But in engineering applications, the phase angle is not critical. Maybe when you do research in some topics, yeah, it can be critical, but the RD, the displacement amplification, and next week we will talk about acceleration and velocity. We will talk about them next week. They are more important and critical to evaluate. So yeah, they are not kind of heavily applied in our work, but again, it's worthwhile to look at. So let's look at the situation when the forcing frequency, again, over the natural frequency of a building is way. Can someone tell me in that building, what does it mean? Does it mean a soft building on gentle ground, or a soft building on abrupt motion? Which one? Can someone just confirm to me what does this situation physically means in terms of building on a ground that being under excitation? Just want you guys to imagine and think, what does this mean? Does it mean a stiff building? Correct. Solid building, a stiff building, wider one? Yes. On what type of motion? On a gentle motion. On a gentle motion. So yeah, and that means a gentle motion. It means this will be very small. Gentle motion, that means the frequency here going to be very small. And because this is to do with the motion, this is to do with the building, and as responded on the messages, it's got very high frequency. If we have very high number here, that will again put us far away. The ratio will be way smaller than 1. So if we have this situation, we're going to be situated here within our phase lag to frequency ratio plot. And that means we're going to be under such arrangement, which we've seen. Remember the first slide when I showed you is kind of saying the same thing. So this topic is the same as the one we're talking about. We're just explaining it to you from different ways. So in such situation, we're going to be just situated here, which it means that there is really no impact in terms of the damping. And again, the phase lag can be very, very small. You can see here, there's no major phase lag difference. Whether there was between me and you, whether there was difference or not, it won't matter for the structural engineers because we're worried about how far it's going to go, not when it's going to go. That's the first situation. The second situation here, it's the opposite to the one we just talked about. So here it's a soft building when it's excited by a motion with very high frequency. So this is very high number and this is very small number, which will result in a very, very large ratio. Where are we going to be situated on this curve? Having very high ratio, we're going to be somewhere here. And yes, with this situation, we're going to have some sort of relationship with the lag. So they're going to be a decent kind of lag difference. Yeah, you can see there's some sort of lag difference, and you can also be impacted or affected by the damping ratios as well. Right? You may have some effects by the damping ratio. Let's say our resonance problem here. Resonance here. So when the forcing frequency is kind of same as the natural frequency or very close to it, then in this case for all the values, so we are here. Well, I don't think you ideally can be somewhere here. You're typically going to be a little bit to the left, a little bit to the right. But in this situation, your phase lag will be a bit smaller than the situation we had before. Which is, again, about 90 degrees in this case. And it won't really then make a difference. You can see here it's only about 90, but this is in radian values. Okay. As I said to you, the most critical, what we always work with is the RD, how the RD going to change with changing this frequency ratio. Right. So that's the notes we have for today. In summary, pay strong attention to the frequency charts, which I took you through, and understand the use of understand the formulas we are using for each situation. So equation number 13, we simply use equation number 13 when we have resonance, right? That's the third case. Case number 2, when we had the gentle building being excited by very rough ground excitation. We use this equation, okay? Case number 1, when we have the stiff building being excited by the gentle motion. We use equation number 11. So understand the equations, and their use depends on the situation we are under, which depends on the relationship between how stiff is the building and how high is the frequency of the exciting motion or harmonic motion. We're talking about harmonic motions this week. All right, so this is the key thing you need to really understand. And this week we just have one simple example to do. We're going to have a little bit more during the workshop, but we're going to have more time to talk about your assignment because I think. So just have a read. Just have a read through this example. And maybe, I think, yeah, we didn't have a break. So have a read through this. And maybe within 8 minutes, I will come back and just talk about this. Then I will give you some general information about your assignment and what we're going to do with it as well. Okay, so 8 minutes or 8 minutes break, and I will come and talk with you after that. Have a read through the example and ask me any question. Just run through the slides. If you have any question there, as I said, pay strong attention to this frequency response curve and the equations that will give us the dynamic response, displacement, deformation response. If you have any questions, let me know. I will come back to you shortly. Okay, any questions? Okay, so what we have here is a single degree of freedom system, and the displacement amplitude, was this dynamic or static? I want answers. Is this dynamic or static? What this character tell you? So from the character here, we can know it is dynamic. So due to harmonic force is known for two excitation frequencies. So what they did, they kind of doing experiment on a single degree of freedom system. It looks like it's a small scale structure, whatever it was. And just from the displacement dynamic deformation, it's really small. So it's not really that large structure. You cannot displace a large structure this big. So they found at forcing frequency, when the forcing frequency was equal to the natural frequency, then the displacement, the dynamic displacement is 127 millimeters. And when the forcing frequency was equal 5 times the natural frequency, then the displacement deformation was 5.5. They're asking you to estimate the damping ratio. So this is again an example which you may be required to determine what's the damping ratio, what's the eta, yeah, for a system. What you do, you're going to take a machine that will be exciting or applying frequencies into a system. Now, from calculations, you will be able to determine the natural frequency of the structure, whether it will, because you're going to know the mass, you're going to know the stiffness, and from these two relationships, you can determine the natural frequency. So what you're going to do first is you're going to try to work with the tool or machine you have, where the frequency is going to be same. And from there, you're going to be measuring the displacement. They found it to be 127 millimeters. And at such relationship, they found it to be only 0.5 millimeter. So you have simply recorded these data from experiment you're doing. And what they simply asking you to do is to find the damping ratio. So which condition we're going to be under, guys, again, for this situation? Condition 1 or 2 or 3? For this condition, we've gone through 3 conditions. Remember the frequency chart? We've gone through 3 conditions. I'm simply asking you which condition we're going to be governed by, 1 or 2 or 3. Very simple, guys. Yeah.
3.
3. Yeah. Well, three. Yeah. The resonance. Correct. Yes, the resonance. So let's see what they did in the solution. They have used this relationship now and formulated an equation 1. From where they got this relationship, have a look to the 3 situations we examined, 1, 2, 3, and this is the one I was talking about because the omegas are same, right? And so we formulated the first equation with our unknown. Then what's happening here? Is it case number 1 or 2 or 3 again? The forcing frequency is 5 times the natural frequency. So in an exam, I may get you a real building, and so you should be able to determine where we are at. So in this line here, we are in what situation?
2.
2. Okay, so the forcing frequency is smaller than the forcing frequency is actually smaller. Is it 2? So alternatively, what you can do, if you divide omega over omega n, is it going to be case 2 or yes or no? I've got an answer 2, but what you can do here, divide the forcing frequency over the natural frequency. It's actually giving us 5. Is that condition 2? Yes, it is actually right. So it's more than 1. That's right. We go back to our RD charts and same thing. So we are able to use this relationship now. Okay, which again, we're going to be situated here. So that's really what we're doing. So the rest is very simple math. We're just having 2 equations, equate them together, and then you got an answer. Now, guys, the really key thing you need to imagine here is how to decide on those. You will be given a scenario. Like here, maybe it was a little bit easy, but in some examples, we may talk about real buildings, like the ones I briefed you about over the lecture. I say if you have a soft building excited by if you want to consider you have a concrete building excited by a soft motion, then you have to know which equation to use. I don't need to give you numbers to determine that, right? Sometimes the question will kind of ask you to go and decide, make a decision on which formula to use based on the information given to you. So it's not always as simple as this example here. We're going to see more examples during the workshop. And as I said, the topic is continuing next week. We'll be talking about the amplification for the acceleration and the amplification for the velocity as well next week, and having more practical examples to practice together. Yeah, the time may not allow for everything today. So this is it for today's topic. So basically, we just looked into that single degree of freedom system when it's excited by harmonic motion, predefined, synthetically defined motion by a sine function or cosine function. The key message from it is you need to know about the RD, the deformation response factor, and know how this is presented in a frequency curve, in a frequency response curve. If you know all these kind of headings I just mentioned, you should be okay and ready for next week's topic. Questions? Now, I've had few meetings with different groups And yeah, it looks like so far, guys, you working with me on the assignment. So what's gonna happen? What's gonna happen tomorrow? We may have another few exams. I'm not sure how many examples we're gonna have to cover. So maybe for 20 or so minutes, that's week 5. Let's see how many examples we have to go through. Yeah, it's only 2. Yeah. So I will just brief you about them. I think they are fully solved for you guys. It's very straightforward topic. Try to go through these examples. And then I will start talking about the second step on your assignments, assignment 1. So I will brief you about the combination process. Now, as per the assignment sheet, you're supposed to be doing this already. By now, I did not brief you about this last week, just because maybe we had a bit more things to cover from the lectures. So during the workshop, maybe only 20 minutes or so to go through these examples. And I think they are really straightforward. Just try to see the ideas here and ask me if you have any, but I'll brief you about them. Then I will start briefing you about the combination process. Then over week 5 or this week, you're supposed to be finishing that. Then the last week, next week, week 6, I will brief you about the final step for your first final submission, which is now going to be postponed for 1 week forward. So next week, it's going to be, again, a progress submission for what I'm going to talk to you about this week. This week, I will show you how to do the combinations of stresses. I'm assuming you mostly have pre-calculated the IXX IYY value. Hopefully that file can open. Let's see if it's here. It's a bit heavy. I don't know why when I open it, it's always don't come very fast. Because maybe I have to download it. Yeah, it's not showing me my writing there. But where we are at is at finding the combination. So, okay, that was what I was exactly talking about. I'm assuming, let me know if you have problems to really find the IXX and IYY value, because each group will have their own values, because each group got their own thicknesses. So look at my video, which is sitting in week 3 section in LMS. There's a video under week 3 section. Follow the steps. You just need to use CAD. It's just going to help you to quickly find the IXX and IYY value. If you want to do it by hand, so be it. Do it if you like. Then once you calculate it, you should be following me. So yeah, that's where you can find it, week 3. Yeah, tomorrow, not tomorrow, Wednesday, I will be briefing the students about finding the stresses. And it's not only about finding the stresses, because those formulas we have in the previous sheets, it's about finding stresses. It's also about how we combine the different loading scenarios in order to find the absolute maximum stress. We have about 10 cases to go through, which I think I will help you with the first ones, and I'm sure the rest will be really smooth and straightforward. It's not a big thing. Then, yeah, the aim from there is to really get into achieve such. It's not very, I don't know why it's super slow. Yeah, I just need to download it maybe. Yeah, that's the aim, is to achieve this distribution. That's really the aim, is to achieve the stress distribution. The red means compression, the green means tension, but we will do this manually, and you're going to be calculating things. Yeah, hopefully by end of next week, and you can submit it just to have a look and give you. Then the final week, week 6, I will brief you about how to calculate the reinforcement. Based on those stresses values, you can calculate the reinforcement, the steel you would need to do. Then by the time you've calculated such values, remember there's another check you need to do about serviceability. And the very final thing, you need to do the drawings. You need to draft the elevations I showed you at the start of the semester. And that will be all combined together from day 1 to the end and submit it to me. Yeah, so the final submission won't be by the end of this week, will be most likely by like the following week. All right, by the end of next week. And I believe after the end of next week, you will have your semester break to go to. All right, so that's our plan. Any questions about our plan? Or any questions about the topic for this week, or any questions about the subjects overall? Okay. Any questions about finding the IXX value? Yeah, this is a bit better. It's very fast to go through. So yeah, this is what I was talking about. Try, guys, to go. If you have problems to understand these equations, also let me know. This is basically mechanics of solids. It's very basic definitions for finding axial stresses. Axial stress, you know, is just dividing the force or the load over the area. And we use this relationship when we have no lateral loads pushing the building. So it's pure dead load coming down the page or down onto the building. We will use it as applicable in over the 10 cases, right? That's one. Number two, the bending stresses. This formula, again, I'm sure you studied it before. What does it give you? It gives you the bending stresses, which is caused by a bending. When you flex the core, you are actually bending it. And how we calculate the stresses? We multiply the moment by y. I'll tell you what y is the distance from the centroid to that edge we want to calculate. So just to give you an explanation, you will be, this is the core. If the centroid is here, y can be, if you are interested to find the stresses at this end, okay, I don't want to put writing here because it's going to destroy this, because if I want to delete it, it's going to take everything away. So imagine with me the centroid going to be here, for example. The y that will be considered when I want to calculate the stresses at this end will be equal to this distance. If I want to find the stresses at this south end, it's going to be this distance. If I want to find stresses at the north end, it's going to be this end, and so on. Okay. Yeah. Now, by the way, where was the south? Was the south the other way? So this should be the south. And this should be the north, is it? That's what we agreed about? Or the north was going down? Can someone to confirm? Was the north going up or down? It should be like this. The north should be this side of the equation. Okay. Any question? So I will take you through those cases, case number 1 all the way to I will support you with those first cases, but you're gonna see really how it's working for the rest, and you should be fine. I had the question about earthquake loading. What was the question again, please?
So if you
let me just put the volume up. I'm not hearing you, unfortunately. Now it's better, yeah.
Yeah, sir. If you could open the code book after the step of finding FI, on the other steps I'm a bit confused about taking the value. So if you could just open the code book AS1170, and
which is here, yeah. Which page you want me to look at?
Lower, sir, lower.
Lower?
Yeah.
That's what you mean?
No, I am done with this step. Further lower than that, sir.
Next. Which page?
P delta effects. Where we find.
What's that? Sorry.
P delta effects.
I can't hear you very well.
P delta effects.
P delta effect.
Yeah.
Why you need to do that?
We don't need to do that.
You mean a different section?
No, here
Which
only.
section?
The torsional effects and other, yeah, P delta effects and yeah.
No, you don't need that. No, that's not. You don't need to do this.
We don't need to do this.
Basically, no. This is what the software gonna do for us. But what I'm asking you to do so far is to calculate the static analysis. That's what we're doing.
Yeah,
that's what we're doing. Yeah. So you okay so far?
Yes, I'm okay with this. And when we are in the STK, it is using the weight as 1000 kilonewton. Yeah. So when we calculated our load, it is different. It is much higher than that.
You have to change it. You have to change structural toolkit. So you change it. Change it to whatever. Just change them. Change all those numbers. Yeah. With me?
Yes, sir.
You change everything similar to what you had. You change the floor heights, you change the levels, you change all that.
All good, sir.
And ideally, you should receive the same value. So the WI, the FI should be same, very, very close.
Sorry, if you can explain me those parameters, G kilonewton and that omega C or Q kilonewton, these parameters little bit.
Which one?
Then previous page, can you go to the EDC2 static?
Yes.
Yeah, here the loads where you kept 0.3 is there. Another thing.
Yes. This is the dead load for each floor. Which you know the table we did together. Here we go. Let me just jump back. You did this table, did you?
Yeah.
This one. Did you do this?
Yes, sir. It's done.
So the overall.
Yeah.
The dead weights, you simply, these are not the final ones, your ones are different, yeah? So take your dead loads and put them here.
Yeah.
Whatever they are. Here maybe 500, let me just use, no, 500, here is maybe 300, here it's 5,000, and the rest should be 5,000.
Yeah.
Yeah, so it's all should be 5,000, you got very simple building there. Yeah?
Yes, sir.
And what about the second one? This one is to do with the combination. I don't mind if you, now this is to do with another standard, 1170.0. So it depends how important it is the building. Is the building is a residential? Then the standard saying to us, you don't need to assume that the building going to be always 100% packed with people, because, you know, like your house or the room you're sitting in, maybe you are the only one there. And in a bedroom, maybe only 2 people there. You know, usually houses are not fully packed with people. It's not like a hospital. It's not like a shopping center. Yeah. So for you, if you took 0.6, it's full mark. If you took 0.3, it's full mark. But if you want to know more about those parameters, go and look at the standard and ask me if you want any help there, but it doesn't matter for me. So usually for residential buildings, we can go with 0.3. The life load, take whatever is here. So overall, take this value, right? Take this value, the overall floor, this one. And I think it should be, not sure, say about 1,000. The first one will be half, about, and the rest will be 1,000. Okay?
Yes.
Now, the rest is just the dimension of the building.
Sir, I have still another question. We are not finding the torsional effects either, yeah? Torsional effects. We are not calculating that.
The what?
Torsional effects.
Torsional. No. No. Yeah, you're not considering it with the static, and that's maybe one of the reasons you want to report about. This is going to be kind of considered with the RCB modeling you're going to be doing later.
All good, sir. And one thing, sir, if you can just open that add submission tab in the LMS so that I can submit the progress of the report.
That's fine. I will just send me email and I will open that to have a look.
All good, sir.
Okay.
Yeah.
Just send me email so I don't miss it.
Yeah.
Any other questions?
Hello, sir.
Yes.
For the value of T1, we should put our own value or consider the value given there?
Is there something I wanted you to agree with me about? Let me double check. What I did, K1 you mean, or?
No, the previous table at there is said that put the value of T1 as it is or use the custom T1. Use custom T1 as no, there is option. Use custom T1.
I'm with you, yeah. Now, is K1, but
Here,
K1 is actually a function of this, isn't it? This is unchangeable, these parameters.
T1 should be the same.
But let's have a look to K1. Let's have a look to K1, what's the standard is saying about it. Can I close it? Now, which page it was defined in the standard? You remember?
For T1, I think.
Anyone is not showing it?
So I think there is a formula for T1 and it is said that 1.25 kT Hn power something.
Here we go. All right. No, I think that's what you're talking about.
Yep. This formula.
It is 0.705. It's a concrete structure and a moment resistance. Yeah.
Yep.
So we're not using, I mean, look, I won't mark students down if they took something else, but they have to know what they've chosen. But by full sense, it's very clear the building was concrete. I know all of us can agree on this.
Yep.
But some students may not know what moment resistance means. Because we are designing this building to be resisted by the core, and the core will be checked for a moment resistance, that means it's a moment resistance. So I can consider this as 0.075. If others have used 0.05.
So in the formula, we need to put the value of the building height and put the power of 0.75.
Yes, that's right. That's right. But make sure structural toolkit is doing the same thing.
So we don't
That's
need to
actually
change
the
we
selection
don't
anyway.
need to change the value of the T1 then.
Well, now it's good. It's already selecting the right one. It's already 0.075 because you selected the moment resistance. So you just select the moment resistance 0.075. Yeah.
Yep.
Yeah. What you need to do, guys, is to make sure whatever parameters you are using here, it's not a software. This is kind of Excel-based program, which is kind of repeating your hand calculations. And it's very useful for you to keep comparing and investigating where is the mistake to get things right. So these values should be same as what you've ended up using with your hand calculations, right? The heights, I know some people may consider 2.6, change them. You have to change those as well. The full height have to be same as what you had. So see, there's an error here because something is not matching. So you have, because maybe in EDS2, I've given it less maximum height, so it's not making sense. So make sure you correctly set up the software. If you are not able to get it done, ask me. Okay, so here I think this is supposed to be 30, but again, I know it's not 30, it's maybe 28, 26 with your example. But see, now it's better here. It has no error because I fixed it here. That was just a blank sheet I opened. It was not. This is not a solution for your work. This is just an example. All right, so make sure you update these grade boxes, same as what you adopted. Okay.
Thank you, sir. Thank you.
All the best. Okay, guys, it's 4 past, so just send me email or we will have some hopefully good time where it's just for you guys to ask me questions Wednesday. All right, we'll see you then.